In this video, we will be studying about 8051 stack, the stack and subroutine instructions, and assembly level programs which involves loops and subroutines. So these are the topics we will be studying in this section. So let us understand what is 8051 stack. So the 8051 stack, as it is mentioned in this diagram here, it's a section of RAM which is used by the CPU to store information temporarily. So when you say it is a section of RAM, we know that 8051 has an internal memory of 128 bytes. So this 128 bytes of internal memory, I am showing it here. This is the internal memory which I am showing it. So now what happens is this 128 bytes of memory which is spanning from the address base address 00 to 7F. So this gives rise to 128 bytes of memory. So 00 to 7F. If you see the internal memory is divided into 3 sections, the lower 32 bytes we generally use it for the register banks. The register bank RB0 to RB3. So there are 4 register banks, and above that we will be having 16 bytes of bit addressable memory, and on top of bit addressable memory, this is around 16 bytes. So here register bank is almost around 32 bytes, and bit addressable memory is around 16 bytes. And finally, we will be having the general purpose memory on top of the RAM, which consequents from the base address 30 to 7F. This will be called as general purpose memory. So this is the basic memory structure of 8051. So now the same space is used for stack also. That is what is meant by the term that is a stack is a section of RAM used by the CPU to store the information temporarily. So now when you say the same memory space is used to store the information temporarily, this kind of information could be a data or an address. When I say data, like suppose our data is residing in some memory location, maybe 7E or something. So here some data is there, 80 or some value inside this 7E address location. So I need to use this memory location 7E for some other purpose, but I don't want to lose this 80 data. So what I will do is, I will push the content of 7E to some other memory location and use this 7E location to store some other value which is other than 80. So when I say I will store this 80 data temporarily to the stack. So the stack is used for storing this data temporarily using some instructions. So now coming back to the definition, we just said that this information could be a data or it can be an address also. When I say address, usually what happens is when you use the subroutine programs, the concept of pushing the address using the call instruction or return instructions is very much important, because the subroutine programs will change the program flow from one particular location to a totally different location. So once a subroutine is executed, we may have to come back to the original program where it was being called from. So that is the reason those addresses has to be saved in the stack. So anyway, so with this idea, let us now understand clearly what are the elements involved in understanding this concept of stack. So we will now move to the definition of a stack. So let me clear all these things. You see this way. Yeah. So we have a memory space here. Now we need to use stack, means we need to use this memory. So whenever we talk about memory, there is something called memory address. So there is a register, there is a special function register which is used in 8051, which is used to access the content, access the address of this memory, and that special function register is called a stack pointer, or in general we will call it as ASP, the stack pointer. So the stack pointer, since the stack pointer is an 8-bit register, so this can hold an address from 00 to FF. So the content of this is like there are 8 bits, like from 1, 2, 3 up to 8 bits are there. So this will hold any values between 00 to FF. So when an 8051 is powered up, or the default value of this stack pointer is 07. So 07 is the default value of stack pointer. As I told, a stack pointer can hold any value between 00 to FF, but the default value of stack pointer is 07. There is a specific reason why it is 07. In a nutshell, we can say stack is a section of the internal RAM. Stack stores the data or address temporarily. There is a special function register called a stack pointer. The stack pointer is used to hold the address of the stack memory, and the reset value or the default value of stack pointer is 07. When it comes to the instructions which is used for accessing the stack or saving the data in the stack, we mainly talk about the push and pop instructions. Even we have a call as well as a return. That is, call can be an L call or a call, and return instructions are also used using the stack memory. However, we will see the call and return instructions when we study about the subroutine concepts. So now we will concentrate on the push and pop instructions. So the push instruction is used to store the content of the CPU register onto the stack. So to store the content to the CPU register onto the stack, this is not only the CPU register, it can be the content of memory also. When I say CPU register, it can be any special function registers like program status word, or it could be the timer mode register, it can be the timer control register. So there are so many special function registers. So we can push the content of those registers to the stack, or even we can push the content of the memory to the stack. And the stack pointer, while pushing, it will store the last used location of the stack. And as we push the data onto the stack pointer is incremented by 1. So we will understand this in detail while explaining some of these examples which is shown below. There is also an instruction to retrieve the contents of the stack back to the register or the memory. This instruction is called the pop instruction. So with every pop instruction, the top byte of the stack is copied to the register specified by the instruction, and the stack pointer is decremented once. So we should understand the pop instruction is used to load the content of the stack back into the memory or the CPU register. Okay, let us clearly understand this with an example what is written below. Look at this example. We have a memory I have mentioned here. This is assumed this is the memory, a section of the memory, and this is a section of the memory. We are using it as stack because I have used the stack pointer address, the default value. I have not changed it. The default value is 07. So I just shown the memory space 07, 08 and 09, and let us assume whatever is the content in this 7, 8 and 9. I'm not bothered right now. Now I wanted to write an instruction push 30h. So when I say push 30h, that means there is some value inside this 30h. Let us assume that 30h contains, these are hexadecimal 30, 31 and 32, which is the address of a section of this internal RAM. Again, this is a RAM. Okay, all these are RAM only, RAM spaces. Remember that. So I won't be repeating that again and again. Everything is RAM. Now, when I say 30, push 30, there is some value. Let us assume that the value of 30 is maybe 8A. 8A is there in 30H. And let us assume that 31 contains 5C, 32 contains 09. There are some random values which is there in the memory location 30, 31 and 32H. The moment I say push 30H, as we already know that the stack pointer is having the value as 07. So if you see the previous explanation, the push operation is before pushing operation, the content of the stack pointer will increment once. That means it is pre-incrementing before the operation. So if the stack pointer is 07, the stack pointer will become 08, and what we are pushing is the content of 30. So the content of 30 is 8AH. So this 8A will be pushed to the location which is having an address specified in the stack pointer, which is 08. So 08 is this memory, and to that location this 8A will be pushed, or it will be temporarily stored. Now when you say, and as we've seen that this push operation is preceded by the increment of the stack pointer, or it is pre-incrementing of the stack pointer. And when you explain this pop instruction, so I am just writing it as pop 30h. What happens is the content of stack pointer is right now it is 08, and it will take the data from 08, as we've seen that 08 contains 8A. Since the data from 08 is being taken it by this pop instruction, and it is moved to the memory specified in the pop location. So when you say pop 30h, this 8A will be moved to 30 location. So we can say 8A will be appearing here. So this is what is happening. But while executing the pop instruction, you've seen that stack pointer was 08. After the instruction execution, after the execution of the pop instruction, the stack pointer will become 07. That means it will do a decrement after the pop instruction. So there are two concepts that is called this is pre-increment for push instruction and post decrement for pop instructions. So pre-increment for push instructions and post decrement for pop instruction. So this is what exactly happening when it comes to push and pop instructions. So now we will see some examples. Let us take this example. In this example, it is written that show the stack and the stack pointer from the following. Assume the default stack area. When you say assume default stack area, means it indicates that SP is equal to 07. And the instructions, if you read through these instructions, the first instruction says that move R6, 25H. So the value 25 is directly immediately moved to the register R6. Similarly, 12 and F3, these are the three immediate data which is moved to R6, R1 and R4 respectively. Remember, it is F3 only, but since usually the compilers or the IDEs what we are using will always expect a number to be in the beginning, so we will use 0 F3, but it's actually move R4 comma F3H. So after this default, after we push some value to the R6, R1 and R4, we have written three instructions: push 6, push 1 and push 4. So when you say push 6, the idea is we are pushing the content of memory location 6, memory location which is having an address 06 to the stack. So when you say here we have defined the stack is having the default address which is 07, and the stack memory will be now definitely from 8 onwards, because SP is 07, stack memory will be from 8 onwards. So I have just mentioned
It's 8:30.
I have just mentioned those memory locations here again. So please remember, this is again internal RAM, as well as this also internal RAM. So a section of this memory is shown here. So remember, since our SP is 07, the stack memory is from 08 onwards. Okay, stack memory is from 08 onwards because of our stack pointer is 07. And since we are pushing the content of 6, 1 and 4, 6, 1 and 4, I am just showing those locations here. 6 is there, 1 is there, and 4 is there. But please remember one thing, this 6, 1 and 4 are also the addresses of the registers in the register bank 0. So if you see 00 is the address of the R0 register, 01 is the address of R1, hence R2. So 04 must be the address of R4 and 06 is the address of R6, which is in the register bank 0. That is why I have used these three instructions. These three instructions, move R6 hash 25 means in 06 or R6 is 06 itself. I will be storing the data 25 in the beginning. Similarly, in R1 we are moving 12. R1 is this one, 12, as well as in R4 we are moving F3. R4, where is R4? Yeah, this is F3. And see, we are using the same locations. If you see push 6, 6 is this address, which is the R6 register itself. So when I say push 6, the content of R6, which is 25, will be pushed to the first stack memory. The 25 will be moving to the 08 location. Why? Because stack pointer is 07, and the moment the push instructions comes, the stack pointer will increment, then that will become 08, and to that location, 08 location, the content of 6 will be moved. So the data which is there in the R6, which is sorry, I'll just remove, it is not 08 here. Yeah, so this 25 will be moving to 8th location, 25. Okay, so this is what is happening in the after the execution of the first line. Now coming to the second line, next line is basically push 1. So when I say push 1, what happens is the content of memory location 1, which is 12, will be pushed to the next stack value, next stack location. Because you know that SP is right now 08. So before this pushing, SP will become 09, and to the 9th location, this 1 will be moved. So this will be going to the 9th location. The content of 1 will be moved. Similarly, when you say push 4, this F3 will be going to the next location, that is, what is the content of F3? Yeah, correct. F3 will be moving here. So this is what is happening when it comes to push operations. Okay, so after this operations, what happens is, earlier this data, the content of 08 was whatever it is. Now it is changed to 25, and this is 12, and this is F3. So this is 6 was 25, 4 was F3, and 1 was R1 was 12. So basically it is pushing the first, whatever is pushed will be pushed to the bottom of the stack, and the stack will increase, and the next pushes will be on top of the stack. So like that, it is keep on pushing. So finally at the end, the content of stack and the stack pointer will be in such a way that we have done 3 pushes. The stack pointer now contains 0A. SP was here, the content of stack pointer was 07, and this was become, before this it was 07, and that has turned to be 08, and when I send the next one, it will become 09, and push 4 will become 0A. So the stack pointer will become a 0A at the end of the 3 pushes, and the content of the stack will be this values. So this is the example what we have seen here now. We have seen how the push instruction works and how the stack pointer content is incremented while executing the push instructions. So now let us see how the pop instruction works. So we will study that with an example. So here we have a section of memory which is shown here. So we are just doing this as a continuation of our previous explanation. So in the previous explanation example, we have seen after all the push instructions, the memory is looking like this. This is the section of the memory, and the same section of the memory is redrawn here for your understanding. So I have just kept the memory location 06, 04, and 01 as some scrap values. But that means maybe after pushing all these instructions, all this data from this register value 06, 1, and 4, I might be using this location for storing some other values, and after some time I will use this pop instructions to retrieve the earlier data which was stored in this location 6, 4, and 1. So to retrieve the data, we are using the pop instructions. So now coming to the explanation. So let us study. Wait, I'll just hold here. Just remove these things. Whatever is the content. Right. Now, when you say look at the sequence at which we are popping. An ideal way, it's not always required to be like this, but an ideal way, if we wanted to restore the values exactly in the same position where it was before, an ideal way of popping is a last in, first out. Last in, first out manner. That means if we push the for last, then we should pop for first. So whichever was last pushed has to be first popped. So last in, first out. So this is how we should do that if we need to retrieve it in the same, we need to retain the values in the same fashion. So what happens here, let us understand. You remember in our earlier explanation, the stack pointer was 0A. The value of stack pointer was 0AH, and When you pop 4, the content of stack pointer is 0A. That memory address 0A will have a value F3, and that F3 will be moved to the location 4. That means this F3 will be moved to location 4. So 4 will contain now F3 after the execution of the pop4 instructions. So pop4 means content of the address which is specified in the stack pointer. That address contains a data. That data will be moved to the address specified by the in the pop instruction. That is 4 is the address. So F3 will be moved to the address location 4. And after the popping instruction, the stack pointer will decrement 1. So stack pointer will become 0, 9 in this case. Now, during the next pop instruction, it is popping 1. So when you say pop 1, now see what is the stack pointer? It is 9. So it will go to the 9th location and see what is the content, which is 12. And that 12 will be popped to address location 1. So this 12 will be moving to address location 1. So this will become 12. And last one is pop 6. So during the previous instruction, that is pop 1, SP was changing to, after that SP will be changing to 0, 8. And when I say pop 6, this 8th location content, which is 25, will be moved to the address specified by the pop instruction, which is 6. So 25 will be moving to location 6. So this will become 25, and SP will decrement, and SP will become now 0, 7. So after the execution of these 3 pop instructions, you see the values of 6 address location is 25, and 4 is F3, and 1 is 12. Hence, we can say that at the end of this 3 instructions, that is pop 4, pop 1, and pop 6, the content of the memory locations 1, 4, and 6 is 12, F3, and 25. If you see, it was earlier, yes, it was 12, F3, and 25 in this. It is the same thing is being retrieved here, and the data is now temporarily saved and retrieved back after the push and pop instruction. Hence, to conclude the today's section, what we have seen in general, we have seen what is a stack, what is a stack pointer, and what are the instructions which is using the stack, that is the push instruction and the pop instruction. Also, we have seen the default value of stack, which is 07, and we have seen that the push instruction is preceded by an incrementing of a stack pointer, and we call it as pre-incrementing, and the pop instruction is followed by a decrement of stack pointer. We call it as post decrement. And if you wanted to change the value of the stack pointer, default value of the stack pointer, we can change that also just by writing some move instruction, move sp comma hash 7 70h. That means the stack will be from 71h onwards. So be very careful when you select the stack location, because you know the internal memory is ranging from 00 to 7f only. In that internal memory, the address location 00 to 07 is for the register bank zeros, R0 to R7, and the bit address location 20 to 2f is basically the bit addressable memory, with addressable memory, and the address location 30 onwards up to 7F is the general purpose memory. And whenever you choose a stack location, general purpose memory, so whenever you use a stack location, make sure that you are not you are doing it sensibly in such a way that by mistake it is not overwriting any of the values of this bit addressable memory or the register bank or even the general purpose which you are using in your program. So suppose if you are not using these locations or a part of these locations in your program, it is fine, you can use that location as the stack, but otherwise be very careful while defining a different location for a stack. So that's the end of this today's session. So if you have any questions regarding this, you can write it in the comments section, or for the students, we have created a Google Classroom, so you can the link of this video will be available in that Google Classroom for your later purposes, and you can comment in that session with your doubts. So thank you, thanks a lot.